Einstein's theory of special relativity. It's counterintuitive, it's weird, and all of its mind-bending complications are often hand-waved away with one of many different, confusing explanations. If you're watching this video, you've probably already watched a lot of other videos on YouTube about special relativity because, well, they don't quite seem to agree on how to explain it. If you're hoping that watching just one more video will make it all make sense, then you might just be in the right place. If you want to explain anything difficult, naturally, you have to use a paradox. You know, to avoid confusion. I promise no math will be required, just a little counting. Let's recount the story. I'll try to be brief. Alice and Bob are twins, hanging out in spaceships. You know, like twins do. Since this is special relativity, space-time is flat and there is no gravity. We'll save that for another video. Alice fires his engines and accelerates to 60% the speed of light. Both of their clocks are perfectly calibrated so they can keep track of how long until they meet again. Alice reaches a prearranged point that is 6 light minutes from Bob. He turns around, accelerates, and returns to Bob again at 60% the speed of light. When they meet, Bob's clock says 20 minutes, but Alice's says 16. What the? Was he speeding? Did he time travel? Okay, what happened? According to Einstein's theory, all motion is relative. So when Alice is traveling away at 60% the speed of light, from his point of view, Bob is traveling away at 60% the speed of light. They both agree on the speed, so that means if Alice traveled for less time, he also had to travel less distance. This is a space-time diagram. Space on one axis and time on the other. The number at the bottom indicates what inertial frame the time axis is in. We'll treat Bob's point of view as the zero-speed reference frame. That means from Bob's reference frame, this is Alice's trip. Out 6 light minutes, and back. Let's just look at the first leg of the trip from Alice's point of view. We'll need to use a Lorentz transformation. Don't worry, I have a calculator. Alice reaches the turnaround point in only 8 minutes, but from Bob's point of view, the journey took 10 minutes. This is exactly what special relativity predicts. As Alice speeds up, for him, time dilates and length contracts. That's why the clocks don't match at the end. Paradox resolved. Done. Tune in for our next video. Einstein's theory also says that both twins can measure the speed of light and get the exact same value. This means there is no absolute frame of reference. Each of the twins can claim the other is moving at increased speed, and therefore the other twin's clock is moving more slowly. To illustrate this, let's add some lines to our diagram that demonstrate light signals that Bob and Alice send to each other. Notice that all of the lines are at a 45-degree angle. The speed of light is constant and remains so, even when we change to Alice's point of view. If Bob and Alice both send a pulse every 2 minutes, we can see that they will each receive a pulse every 4 minutes. You may have heard this explained as they both see the other's clock moving slowly. Well, duh, that's the Doppler effect. Yes, it is, but not only that. If it was only the normal Doppler effect, then the relative speed of the signal would depend on the medium that the signals go through. Like sound waves traveling through air. The red and blue shifts would be different for each observer, and they would send and receive the same number of signals by the end of the trip. In other words, the time dilation would be apparent, but not actual. On the other hand, the relativistic Doppler effect accounts for the fact that the speed of light is the same in all frames of reference. This means that the time dilation must actually occur. But then I just said both of them receive a pulse every 4 minutes. The same speed, the same Doppler shift, the same time dilation. One of the twins must travel a shorter time and distance than the other, but if all motion is relative, how do we know which one? This is where the real paradox comes in, and unfortunately where the explanations tend to go off the rails. You may have heard, something breaks the symmetry.
It's the acceleration!
No, it's the force. No, it's changing inertial frames.
It's rotating your notion of simultaneous time!
It's the ether, you jagoff!
And they're all right, sort of, but they're also all confusing. Sabina says that
acceleration is absolute,
and
the reason time slows down is acceleration.
Minute Physics says something else.
But because of your change in velocity when you turn around to come home, your notion of time rotates and skips right over a large swath of my time.
I don't even know what that means. Physics Girl seems to agree, but gives a different reason why.
It's during this period of acceleration that you become the older twin. But we have to use a different set of rules from general relativity.
Wait, the time dilation occurs instantaneously at the turnaround? What if Alice goes further away? If he travels for 10 times the distance but makes the same turnaround, the same acceleration, there still has to be 10 times the dilation. How does his clock know how much time to skip? They are all saying that a single moment of acceleration breaks the symmetry, no matter how far Alice travels. But how? Time out. Let's clearly define our terms. From now on, when I say acceleration, I mean a change of velocity, which is apparent, not absolute. Since velocity is relative, acceleration must be too. We could even accelerate our whole frame of reference, although then it technically becomes non-inertial. And we can see this in the space-time diagram. Look at the turnaround. Bob sees Alice go from 60% of the speed of light away to 60% of the speed of light towards him, a change of 1.2 times the speed of light. But in another reference frame, like Alice's first frame, the acceleration is different. It's 88% of the speed of light. Now you could argue the amount is relative, but not who experiences it. In that case, what these well-intentioned YouTubers are really talking about is not acceleration, but change of momentum. They are talking about a force.
I feel something.
You feel it?
Yes, I feel it.
That's the force.
Really?
Wow, it must be really strong
Oh,
with
I've
you.
never felt any... Ow!
Now with a spring or a bucket, we can tell who is accelerating, changing momentum, and that somehow breaks the symmetry? What if we forgot our spring and bucket? What if all we have is data or video evidence? If you can't tell who is changing momentum, the symmetry remains intact, as does the paradox. Now, if we can't measure force, and acceleration is relative, then our twin paradox journey would have to be equivalent in these three scenarios. 1. Alice goes out and comes back. 2. Bob goes out and comes back. 3. They both go out and come back. In order to resolve the paradox, we need to prove that these three cases are in fact different, and we need to do it without invoking force or acceleration. Can we even demonstrate the paradox without any acceleration? Yes, we can. 3 reference frames and 3 spaceships. Triplets! We'll again build this adapted scenario from Bob's frame of reference. It goes like this. Alice heads out from Bob at a constant speed, 60% the speed of light. Alice intersects with Carol at the prearranged point and is going 60% the speed of light the other way. Alice hands off his clock time to Carol, and Carol continues measuring time until she reaches Bob. Just like before, everyone is sending a signal every 2 minutes, and we see the appropriate Doppler shifts. Bob sent 10 signals between Alice leaving and Carol arriving. Alice clocked 8 minutes until he met Carol, and it also took Carol 8 minutes to reach Bob. It worked. No acceleration needed. We just changed inertial frames, right, Dr. Lincoln?
Observer A existed in one and only one reference frame. The moving observers existed in 2. That's the only difference.
So it is changing inertial frames that breaks the symmetry. By using the Lorentz transform, we can see that changing reference frames does change the relative velocities, but we can still see where the inertial reference frames changed. The bend never flattens. We can look from any inertial frame, from any outside observer, and get the same result. Symmetry broken. Paradox resolved. Right, dialect?
What even defines an inertial frame? If you define inertial frames via the absence of acceleration, then to switch between two inertial frames simply means to accelerate. The whole one-frame, two-frame formulation is just kind of a complicated way of saying that one twin experiences force while the other doesn't. Their definition of an inertial frame, meanwhile, becomes implicitly characterized by an absence of any known force-producing sources that could be acting on the system.
What if our entire concept of an inertial frame is also relative? We defined Bob's reference frame as inertial because it helps us solve the paradox, but how do we know it actually is inertial? We defined inertial frame by deciding who accelerated, but if inertial frames are defined by not accelerating, and accelerating is defined as changing inertial frames, then our logic is circular. Let's try a definition from TED-Ed.
To be an inertial observer, one has to maintain a constant speed and direction relative to the rest of the universe.
There's that word again. Relative. How do we know the entire universe isn't moving or accelerating or spreading out or spinning? We can solve the paradox because we defined the inertial frames and chose flat spacetime. These inertial frames are a construct. We made them all up. The twins, the outside observers, all of it. If we were to conduct an experiment in real life, how would we know which reference frame is actually inertial and which is not? What if we only had video evidence from each of the twins? Is there a way to tell who is changing reference frames, whose clock is slower, and without invoking acceleration or force or constructed reference frames? Yes, there is. Roll that beautiful bean footage. Pay attention to the number of flashes they receive. They received a different number of flashes. But did you catch the other difference? Back to our diagram. The key is to follow their timing signals. On this diagram, each send and receive point is an event in spacetime. No matter what inertial frame we observe from, the events are always connected by 45-degree lines. The speed of light is preserved, as well as the structure. The lines never change order. They shrink and expand, but never rearrange. Let's follow our videotapes again along with the diagram. They both begin with a red shift. Alice's video of Bob changes from red to blue when Alice turns around. And what about Bob? What does he see? Because of the distance, Bob sees the change to blue shift after a delay. Let's flatten Alice's timeline. This is the correct way to draw the diagram from Alice's entire point of view. We get this strange discontinuity in the diagram. In reality, there would be a continuous transition, but for simplicity, we allowed Alice to instantaneously accelerate, which is not actually possible. In any case, this is not equivalent to this. It's not the same. The twins cannot both arbitrarily claim they were stationary and therefore be the older twin, and they can tell what happened without ever meeting again. We know who changed inertial frames based on the timing of their red and blue shifts. There is only one way to organize those events, and all points of view must agree. We can change reference frames however we want, but the order of events must always remain the same because the same events in spacetime are always connected. Every reference frame agrees that Bob sent 10 signals while Alice sent 8. The only way to make it so Bob ages less is to change the scenario, which means Bob and Alice will see different things. There is no symmetry. There never was. There is no paradox.
There is no spoon.
So, the twin paradox isn't really a paradox at all. When it is described fully, the asymmetry is revealed. But there's another interesting detail that is often overlooked in explanations of special relativity. Every journey that our twins could possibly take between the two events marking the meeting points are exactly the same space-time distance apart. No matter what path you take to connect them, the distance never changes. Remember when we asked, where did that time go?
Where'd all the time go?
It went into space. Literally. In our twin scenario, Alice traveled 8 minutes in time and Bob 10 minutes. So where did those 2 minutes go? Easy. In the 6 light minutes of space that Alice traveled. Wait. Forking math. Wait. Time is an axis, orthogonal to space. A little Pythagoras.
Holy mother forking shirtbags.
It's not the acceleration, or the force, or the inertial frame that breaks the symmetry. It's the path. Now I know what you're thinking. Position is relative, so the path doesn't break the symmetry. But you're wrong. Position in space alone is relative, but not position in space-time. Each position that Alice and Bob traveled on was a unique event in space-time, a 4-dimensional coordinate, each connected by a specific geometry that is absolute. Your path along those events is what determines your relative position, age, speed, acceleration, all of it. And of course, the path is determined by how you accelerate, change momentum, thus traveling in multiple inertial frames. So all those other videos are right too. Ish. If you pick any 2 space-time coordinates, any 2 events that are within each other's light cone, they are connected by an infinite number of paths. Each path has the same total length in space-time, but only one path connects those events in a purely time-like manner. If I follow that unique path, I stay in that one frame and I experience the maximum amount of time. If I take any other path, then I go through more space and therefore less time to arrive at the second event. I age less, just like Alice, and I can see it in the red and blue shift. We can demonstrate this in our other non-equivalent scenario, the one that actually is symmetric. When Alice and Bob both go out 3 light minutes and come back, there is a path between them that is inertial and where time runs faster. The inertial path takes 18 minutes, while Bob and Alice would both take just under 17 minutes. For the mathematically inclined, this is called the principle of least action, or stationary action principle. And these paths also exist in general relativity. We call them geodesic. Along each path is an inertial frame, a maximum time, zero space path. And this is how every event in all of space-time is connected. This is the geometry that defines all space-time and how we travel through it. It is objective, absolute, and not paradoxical. So that's it. The twin paradox isn't a paradox. Space-time is consistent and objective. Relativity doesn't cause paradoxes in causality, it actually prevents them. Bad explanations, on the other hand, result in lots of YouTube videos, the real paradox being that the more explainer videos on a topic, the less people seem to understand it. Going forward, I think that when we talk about relativistic motion, we need to change the way we talk about distance and now or the present. And then we need to rethink the rules of how we talk about traveling in our universe. This will help alleviate a lot of the confusion. If you enjoyed this video and would like to see more, please like and leave a comment. I plan to add some addendum videos to talk about how to read a space-time diagram, how does uniform acceleration work, and eventually getting to general relativity. So stay tuned and be sure to subscribe. Until next time, try to explain complex topics without using paradoxes.